Limits are the beginning to calculus. Typically, it would be written as the limit of x as x approaches n of f of x. That's just how I wrote it. It just basically says that how does a graph behave or a function behave as we approach some sort of point. So, for instance, if we say f of x is equal to x plus 2 and set n is equal to 3, then we can rewrite this as this, which is basically just saying the limit as x approaches 3 of x plus 2. This is a very simplified example, and here we can just plug in 3 to this, which gives us 5. So as this function approaches 3, it will go to 5. We can also look at left hand and right hand limits. So when we say 3 plus, we're approaching from the right hand side of the graph. So for this instance, I drew a very awful graph, but it would be what would happen at around this point. This point. This x is equal to 3, y is equal to 5. Not a very good graph, but it's there. So if we come from the right, we're coming from this direction. And we could just plug in values that are a little bit bigger. Write that in another color. So this, when it comes from the right, it's numbers that are slightly bigger than 3, like that. 3.1, 3.01, 3.001, and I'm not gonna write all the whole things out, but it's basically that. 3.1 plus 2, yada yada yada. Now when we go from the left hand side, this is all coming from the left hand side now. We're coming from this direction, and we're going to be choosing, and it's written like that with the minus. And now we're going to be plugging in values of x that are slightly smaller than 3. So 2.9, 2.99, 2.999. And when you add it in, it's just getting closer and closer to 5. So because these both are going to 5, they converge to 5, and it really just means that the limit exists. We could say that when a limit doesn't exist is when the left-hand side and the right-hand side do not equal each other, or they don't converge to the same point. For example, if we have f of x is equal to 1 over x, and when we graph this, it's in this sort of shape. And clearly from the graph we can already see that the graphs go off in different directions, particularly right here and right here. So if we want to find the behavior as this function approaches 0, we cannot simply put a 0 in there, because dividing by 0 is a cardinal sin in mathematics. It's not allowed. But we can look at the behavior from the left and the right. So if we plug in, say, from the 0, from the right hand side, I mean, we're getting values that are going to be going in this positive y direction, and we can see that in the graph. So if we plug in, say, 0.1, 0.01, 0.001, and these are just going to be powers of 10. So if we have 1 over 0.1, 1 divided by 0.1, we can say, okay, well, that's just 10 to the negative 1, and then rewriting that as 10 to the negative of 1, which is just 10 to the 1. So that just is equal to 10. Same logic with that, so just 10 squared and 10 cubed. So this, as we approach from the right, is going to be going towards infinity. And with that same logic, now we're approaching from the left-hand side. So we would plug in numbers that are slightly smaller than 0. So like negative 0.1, negative 0.01, etc. And these are just the negative values, negative 10, negative 100, negative 1,000. So you can see that it just goes towards negative infinity. So we can say that this limit, DNE, or does not exist. Sometimes, however, we'll have a graph where there doesn't seem to be, well, continuity in mathematics basically means that we can draw the function without ever lifting our pencil. But if we have to lift our pencil, say go here and then here, for some reason there's some sort of gap right there, that's a discontinuity, and we can figure out how the function would behave as we get closer and closer to these points right here, to whatever's inside here, or this exact point where it stops. Of course, sometimes that hole is a hole and there can never be a value in there. I'll have an example right now. So for example, if we have f of x is equal to, let's say, x squared minus 1 over x minus 1. Using a little bit of algebra, we could see that this numerator here is a perfect square, and factoring that, we can get this, and we are allowed to cancel that. So it would be something like this, but x cannot equal 1 because that would be division by 0. Even though we canceled the terms out, you still cannot do that. So let's say we want to find out what happens at this point, x is equal to 1. Well, we can take the limit. Trying to get my eraser. There we go. So okay, I rewrote it. The limit as x approaches 1 of x squared minus 1 over x minus 1. If we were to plug in 1 for this instance, 1 minus 1 over 1 minus 1, or 1 squared to be precise, this gives us 0 over 0, and that is an indeterminate. It's not even just division by 0, it's just 0 over 0. We can't really understand what that means. So we can look at the behavior from the left and the right. So we can plug in numbers that are slightly bigger than 1, so 1.1, 1.01, and working that out gives 2.1 and 2.01. If we go from the left side, now we're putting in values that are slightly smaller, so like 0.9, and this would be a negative over a negative, which becomes a positive. And this gets closer and closer to 2 also. Follows the same behavior. 0.99. As we get closer and closer to 1 from the left and the right, we see that it converges to 2. But we can also just look at it a little more algebraically. So say we have something like this. We can do this. Oops, not the squared. Cancel those out, and then just the limit as x approaches 1 of x plus 1, which would be, now we can plug it in, and that's 1 plus 1, and that's just 2. And if we were to look at the graph of this, and just graphing this, just something like that, but now when we go to x is equal to 1, now we have this hole right there, and just keeps going on like that. As we get closer and closer, it gets closer and closer to 2, but it never actually reaches that value. Anyway, that's about it. Thanks for watching.